Hello everyone. So welcome to this lecture on electromagnetic induction. In today's lecture we are going to talk about motional EMF. The motional EMF is a very important concept of the Faraday's law. Now Faraday's law has to be valid, and it is valid as long as the magnetic flux linked with a coil is changing. Now this change of magnetic flux linked with a coil can be brought about either by the motion of the conductor in a constant magnetic field or by changing the magnetic field with a stationary conductor, or you can do both of these happening simultaneously. Now if a conductor is moving in a constant magnetic field, then whatever EMF is actually produced or induced rather in that conductor is known as the motional EMF. So very briefly, or in a simple sense, if we have to understand this, we can say if the EMF induced is because of the motion of the conductor in a constant magnetic field, then it is motional EMF. So motional EMF, we can have an expression of the EMF. We can derive it rather. So for that reason, let us consider this particular diagram as shown in this figure. So there is a conductor. So this part is a conducting rod. This is a conducting rod which is moving with a uniform velocity v in a magnetic field. Now see the magnetic field structure which has been put it as cross. Now the cross, as already we know that it is going into the plane of this paper. So if we would have given it like this, in that case it is coming out. So this is coming out, and this means going in. Now these two nomenclature or these two terminologies or symbolic representations rather, you should understand and you should always remember. Now these two are the rails. I mean MSRN, we can say this particular part is a rail which is also a conducting rail. So let's just consider a conducting rod PQ placed in a magnetic field. The magnetic field is going into the plane of this paper. The rod has been placed on the rails PS and QR. Rails PS and QR means this is one rail, this is another rail, and by the way this is also connected. I mean, so you have got a conducting rails all around this conductor P and Q, and as soon as this conductor PQ is placed on this rail, this becomes a complete coil or complete circuit or complete loop because all are conductors. So what you have, whenever this PQ rod it moves in this particular direction, then we can say that the magnetic flux linked with the coil is changing. Now remember, in this case the magnetic field has been put as uniform. That means magnetic field is not at all changing its value, and its density, magnetic flux density basically, is also remaining constant and uniform all throughout this volume. Now let's consider the length of this side. The RS is L, and RQ, the distance between the conducting rod and this rail SR, is equal to X. Now by the way, here L remains as a constant because it is the length, or rather the breadth of this rectangular loop PQRS, and X is the distance between R and Q, which is a variable. Why it is a variable? Because as soon as the conductor PQ moves leftward, the distance X is reduced. So this is why this is a variable. So I hope this diagram is clear from this slide. Next, so therefore what is the magnetic flux associated with this coil? I can write it as phi B, that's equal to B and A. Now remember, in this case magnetic flux linked with a coil is generally given by integration of B dot ds. That's what is a common notion. So in this case, since I am writing A to represent the area, so I am writing it as dA. So if magnetic field is constant or uniform, in that case I can write it as a B dA cos of theta. Now in this case the theta, which is the angle between the area vector and the magnetic field, is 0 because area is also pointing into the plane of this page, and magnetic field is also into the plane of this page. So angle made by the area vector and the magnetic field is 0. So if we put the value of theta to be 0, then cos 0 is equal to 1. So you remain with integration of B dA. So since B is constant, it comes out of the integration sign. You remain as B integration dA, which is ultimately B into A. So this is actually the derivation from where we can write it. Now If A is the area of this rectangular loop, then I can write A to be is equal to the length L, or basically it is actually the breadth into the length, which is x. So that is the reason why I have written it BLX. Now, the EMF induced will be given by minus of d phi b upon dt. This is in accordance with the Faraday's law. So by now you have understood that Faraday's law we are applying at every step. Whenever we want to prove something in this particular chapter, Faraday's law acts as a very basic principle in our path or in our journey. So if you put this BLX in place of phi b, then you are going to get minus of ddt whole into BLX. Now B and L both are constant, so that comes out of the differentiation. So minus BL, you remain with a term dx dt. Now dx dt means what? Dx dt means the rate of change of this distance x with time. Now with time, of course, since this rod is moving leftward, the distance x will reduce. So that means the velocity and the distance, they have got an opposite relationship. That means x increases in this direction, whereas the velocity is pointing to this direction. So the directions of the distance x and the velocity happens to be opposite of each other. So that is the reason why dx dt is written to be minus of v, because x increases in the right direction, but v increases, the velocity not increases actually, but the velocity is in the left direction, because we have considered uniform velocity. So there is no concept of acceleration in this case. The rod is not accelerating, it is just moving at a constant speed v. All right, but it contains an opposite relation with the distance. So that is why I have put here minus v, and this minus minus gets cancelled, so you remain with BLV. So this is the expression of the motional EMF whenever this conducting rod PQ move in the left direction. Now this is one way of deriving this particular expression of motional EMF. There is one more way of deriving it which can be easily proved. You can follow either of them. So this is another way of deriving this. We can also obtain the expression of the motional EMF from the consideration of the Lorentz force. Now what is meant by a Lorentz force? Lorentz force means, suppose I have got a charged particle, say positive charged particle Q, which is moving in a particular direction V. So this is the direction of its velocity. Now let's suppose there is a magnetic field which is making an angle theta with the direction of motion of the charged particle Q. In that case, Lorentz force is given by the expression F, which is equal to Q whole into V cross B, and this force is directed perpendicular to both velocity and the magnetic field vector. Alright, so if velocity vector and the magnetic field vector, these are the coplanar vector, that means they are in a plane, then Lorentz force acts perpendicular to this plane. That's a very peculiar concept. Now in this case, what happens? In this case, you can see these particular rod will contain the electrons which are basically moving, okay, because this is a conducting rod, so the electron will move. So in that case, the Lorentz force acting on those electrons will be given by Q whole into V cross B. Acha, forget about the electrons. We have not classified it yet that these are electrons because I have considered it to be Q. If I specifically consider electron, then I should have put Q is equal to minus of E. But this is something that I have till now not considered. I want to just find a generalized expression of the induced EMF, induced motional EMF rather. So let's consider the charged particles within this conductor PQ which are in motion, and if the charged particle are in motion in a magnetic field, in that case Lorentz forces act, that is a common thing. And if Lorentz force act, then the force is given by F is equal to Q whole into V cross B, but V is perpendicular to B. So in this case, you see the velocity vector is in this particular direction and the magnetic field happens to be in a direction perpendicular to this. So I cannot show this, but you can imagine that V is a right angle, V is at right angle to the magnetic field. So if it is so, in that case, uh, in that case, F, the magnitude of F is given by Q into V cross Q VB. Why it is basically because theta is equal to 90 degree. Theta means the angle between the velocity vector and the magnetic field vector. So if you just simplify this cross product, this will give you q v b sine of theta. So if you put theta to be 90 degree, sine 90 is equal to 1. So you remain with only qvv term. So that is why I have written the magnitude of the force to be qvb. Clear? Now, the work done in moving this charge from P to Q is given by, what it is given by? It is given by W is equal to QVBL. By the way, at this point it is important to discuss about the direction of this force, or rather the Lorentz force F. Now Lorentz force will be acting on which direction? The charges, conductor is moving in this particular direction, so are the charges which are moving in this particular direction, because they are confined by the conductor. So as the conductor is moving, that means the free electrons which are there inside the conductor, they are also basically moving. All right. So what happens if you stretch your finger towards this direction of V and curl it towards the magnetic field B? In that case, you will see your thumb will point in this particular direction. Okay, so that is basically the direction of the force being applied. All right, Q into V cross B, which gives the Lorentz force. What is the direction of that force? Direction of the force is from P to Q. Okay, now if it is so, in that case, the work done in moving the charges from P to Q, I mean, because of this particular force, the free electrons will drift in the PQ lengthwise. That means the free electrons will be getting deviated either from P side to Q side or Q side to P side. All right, I mean, the direction will of course depend upon this charge consideration, which I have said I have not considered yet. I have considered it to be positively charged. So I just considered the magnitude of this particular force. So I'm not considered, or I'm not bothered about the directionality of these things, but I know that the force is acting lengthwise in the PQ direction. All right. So because of that, what is the work done? Work done will be force multiplied by the distance. Now I know that length of PQ is given by L. So you just take a product of this force F multiplied by the L. So that will give us the work done in displacing a charge in the length PQ. Now if this is the work done upon a charge to displace it from P to Q, in that case what will be the EMF? EMF will be given by work done per unit charge. That is what is a basic definition of EMF, that how much work is to be done to displace a charge from one point to another. So in that case, work done per unit charge is given by W upon Q. So if I make this division, I remain with VBL. So this is coincidentally the same expression as we received from the previous expression here, where I considered the Faraday's law directly and calculated the flux associated with the with this circuit, how it is changing. From there we found out the motional EMF expression and we got it to be same. So there are two ways of doing, or two ways of getting this expression of motional EMF. You can follow either of them. Hopefully, because we are doing it in a Faraday's law sense, so the first one I would rather prefer to do. Next, that motional EMF is generated and this particular conductor PQ is moving in the left direction. Whether do we have any relation or whether do we have any conservation of energy? So let us see that. So let us once again consider this rod PQ, which is a conducting rod, and let's now consider that it has got a resistance R, small r by the way. Now resistance R it has, that means whenever the current tries to flow, it offers some kind of a resistance. Now we have also considered that the other arms of this loop PQRS, they do not have any resistance, means this particular arm it doesn't have a resistance, this arm it doesn't have a resistance, or this arm it also doesn't have any resistance or negligible resistance. But PQ has got sufficient resistance, small r, or which is an appreciable amount. So in that case, if I be the current flowing in this loop because of change of flux and the induced EMF, in that case what will be the value of this current I? That will be given by the ratio of the induced EMF to the resistance value. So I is equal to induced EMF expression already we have got to be BLV. So I have put it to be BLV upon R. Now once again I have to consider this Lorentz force kind of a thing. Now due to the presence of magnetic field, there will be a force acting on the arm PQ. Now this force is given by I whole into L cross B. Now these expressions will become clear to you whenever you will read the magnetic field chapter well, or what is the magnetic force whenever a conductor moves in a magnetic field. So these expressions actually come from there. So this force which is acting on the conductor PQ is given by I whole into L cross B. Now remember, L I have considered to be positive in this direction. Alright. So what you have to do in order to find the direction of this force, just stretch your finger towards this length L, curl it towards B, and you see your thumb will point in this direction. This is your thumb direction. So this particular force acts completely opposite to this velocity. Alright. So the conductor is moving leftward. However, the force acting on this arm PQ is in the rightward direction. Therefore, the angle, by the way, the angle between the length vector and the magnetic field vector is 90 degrees. This is quite clear from this figure, and hence the magnitude of this force is given by F is equal to ILB. This is quite according to the previous derivation that we did, L cross B, you break it apart into LB sine of theta. Theta is 90 degrees, so sine 90 equal to 1. This becomes ILB. Now expression of I is equal to BLV by R. So if you put it, you will get B square L square B upon R. Now, if you are moving this conductor in this direction, however, the conductor is experiencing a force in the rightward direction because of its motion in the magnetic field B, then you have to do some work against this particular force. And what is the rate of that work done? The rate of that work done is given by the power that you have to spend in order to move this conductor from right hand side to the left hand side. So that is basically given by the product of Fv, the force multiplied by the velocity. So if you put the expression of force and V, then you remain with B square L square V square upon R. But you have to remember, this is a mechanical work done. Why? Because somebody is moving this conductor from the right hand side direction to the left hand side direction. Somebody must spend his energy to move it. It cannot move all its own. So this is a mechanical work done. But the question is, where does this mechanical energy go? You have spent some mechanical energy, but if you consider this whole system to be a closed system, as if uh, none of the energy escape from this system and none of the energy come into the system, in that case, where this mechanical expenditure of energy go? So this answer is it is dissipated as Joule's heat. How? Joule's heat is given by I square RT. By the way, what is Joule's heat? Whenever you have got a current in a circuit, in that case, there is a heating effect because of the resistance of the conductor, and in that case, the power is given by I square RT. There is a time factor also, but in this case, we have considered the time to be is equal to 1 second. So I have just put I square R. That there is a T also, that T I have considered to be 1 second. So I square R, if you calculate, you see you get the same expression as you got in the previous case. So this is the mechanical energy you spend, and this is the amount of joules heating or joules energy, heating energy basically, which has been produced. So your mechanical energy which is spent to move the rod in this magnetic field with a velocity v from right hand side to the left hand side is getting converted into heat energy, or rather joules heat energy, which has got same expression. So what is actually the chronology of conversion of energy? That's given by your mechanical energy that gets converted into electrical energy, which ultimately got converted into the thermal energy, because Joule's heating effect is only possible if you have got some amount of electrical energy. So in order to do that, your mechanical energy can never be converted directly into your thermal energy. It must be converted into electrical energy first and then thermal energy. I hope this part is clear. So this shows that whenever your conductor moves in this magnetic field, energy also remains constant. So that's all I had for today. Thank you so much. Please go through this particular slide. There are a lot of expressions and considerations. Things must be clear in your mind, otherwise you may confuse. So if you have any doubts and confusions, you can ask, of course. So thank you. Thank you once again.